So, let us next discuss the notion of subspaces which are invariant under a given linear transformation. We will use that notion to prove a very celebrated theorem called the Cayley-Hamilton theorem. So, let us begin by defining the notion of a subspace which is invariant under a given linear transformation. So, definition. So, let T be a linear operator, let T be a linear transformation, it is the same as a linear operator from a vector space to itself we say that subspace W is invariant under T if it is preserved by T, or in other words, if every vector of W is sent to W itself, then it is called as a subspace which is invariant under T. So, a subspace W is said to be invariant under T or T invariant, both terminologies are used, if TV belongs to W for all V in capital W. So, the compact way of saying this is that T of W is contained in W. So, let us look at a few examples. The first example we would like to consider is always the 0 vector space. So, 0 is a T invariant subspace, 0 vector subspace is T invariant for every linear operator T. So, notice that the invariance, the property of invariance is dependent on T. If T changes, if you take a subspace of R, say Rn, which is invariant under one operator, it need not be invariant under a different operator. However, 0 is a 0 vector space, or the 0 subspace is a subspace which is T invariant under every linear operator. So is the entire vector space. V is T invariant for every linear operator T. Right. So, what more? So, given any linear operator, consider W to be the null space of T. Then notice that TV is equal to 0 for every V in W, and 0 in particular belongs to W, and therefore, it is trivially a T invariant subspace. In the same in a similar vein, R of T, W equal to R of T, which is the range of T, is a T invariant subspace. Okay, so more examples. So, let lambda be an eigenvalue. Or let me put it this way, let V be an eigenvector. With eigenvalue lambda. And then let W be the span of the set consisting of V, S is V, say. So, span of one vector. So, this consists of all vectors of the type A times V, and what is going to be T of A times V by linearity? This is A lambda V, which is equal to lambda times AV, which you notice again belongs to the span of V itself. So, hence W is T invariant. In fact, we could have said more. We could have said that E lambda, the eigenspace corresponding to lambda, is T invariant. Same argument given in example 5 will tell us that E lambda is also T invariant. So, one reason why we should be considering T invariant subspaces is because you take the linear operator T and restrict it to the subspace W, and we can think of it as a linear operator on W. So, if T restricted to W is the restriction of T to the subspace W, then T restricted to W is a linear operator on W. So, T restricted to W can be studied as a independent linear operator which is operating on the subspace W. So, let us prove a theorem to indicate that this is quite useful. So, let T be a linear operator on V and W be a T invariant subspace. Then the characteristic polynomial of T restricted to W divides the characteristic polynomial. So, let me just write CHAR for characteristic and POLY for polynomial of T. So, let us look at a proof. So, this theorem tells us that by studying the restriction of the linear operator to an invariant subspace, we get some information about the characteristic polynomial. We get a hold of at least one factor of the characteristic polynomial. Okay, let us look at a proof of this. So, let us start with a basis for our subspace W. So, let alpha equal to V1 to Vk be an ordered basis of W. Now, this is a linearly independent set. Now, this is a linearly independent set which is sitting in capital V, and hence it will be sitting inside a basis. So, extend this to a basis and beta equal to V1 to Vk, Vk plus 1 to Vn. Okay, so let me add at this point that even though I am not writing it, we will consider only finite dimensional vector spaces. So, let me write here that it is a linear operator on finite dimensional. We are indeed talking about the characteristic polynomials. Let me write V dot S for vector space, but nevertheless let me put it in the criterion. Okay, so beta be obtained by extending our basis alpha. Beta be a basis of V, beta be a basis of, again ordered basis of V. And let us look at T W with respect to alpha. That will be, let us say that is some matrix B. Okay. Then let us now look at what is t with respect to beta. I leave it to you to check that this will be a matrix B, which is of course k cross k matrix, a k cross k matrix, and there will be a 0 matrix consisting of n minus k cross k vector, elements, and then there is a C and there is a D. C is k cross n minus k, and this is going to be the n minus k cross n minus k. So, this is how the matrix of T with respect to beta will behave. So, to talk about the characteristic polynomial, we have to look at the determinant of, so let f of lambda be the characteristic polynomial of T and g of lambda be the characteristic polynomial of T restricted to W. So, let us call these things this as A. So, g of lambda or rather f of lambda is equal to determinant of A minus lambda I n, and g of lambda is equal to determinant of B minus lambda I k. Okay, let us analyze what is determinant of A minus lambda I n will be. This is equal to, this is what f lambda is, right? This is equal to determinant of, so let us look at what A is. A has 4 blocks, the bottom block has a 0, left bottom block, and the right top block will not be affected at all by subtracting lambda I. So, this is just going to be B minus lambda I k, there will be a C, there will be a 0 here, and there will be T minus lambda I n minus k. And we know exactly what this determinant is by one of the exercises earlier. This is just going to be equal to the determinant of B minus lambda I k times the determinant of D minus lambda I n minus k. But what is this? You notice this is equal to g of lambda, and this is going to be some polynomial p of lambda, and hence g of lambda divides f of lambda. We have done, or we are done with the proof. So, if we have a subspace W which is invariant under T, and if we restrict our attention to T to W and look at the characteristic polynomial there, it divides the characteristic polynomial of T itself. We will use this result and a few more other observations to very particular subspaces of V which are invariant under T. So, let us look at one more example, another example. Example of T invariant subspaces of a T invariant subspace. So, let V be a vector in capital V, then let W and define W to be the span of V, TV, T2V and so on. So, what is T2V? Where TKV is just T of T of T of TV. Notice that T is a linear operator from V to itself. So, TV is a vector in capital V. So, we can apply T to TV, that will be T square V. TKV is similarly done k times. So, get hold of a vector V and look at all powers of T applied to V, and then look at the span of this. Then I will leave it as an exercise for you. W is invariant under T. And definition, the vector space, the subspace W is called the T cyclic subgroup, T cyclic subspace generated by V. The subspace W is called the T cyclic subspace generated by small v. So, what can we say about this particular T cyclic subspace, this particular T invariant subspace? This T invariant subspace has some very nice properties. The first among them is that we have a very good control over what the basis of such a subspace is, and secondly, we know how the characteristic polynomial looks like when T is restricted to W. So, let us prove a theorem which captures all the information which I just said. So, let W be a T cyclic subspace generated by small v. Suppose dimension of W is equal to say k, then V T V up to T k minus 1 V is a basis of W. You know exactly what the basis of W will look like. Not just that, moreover, if so T to the power k V will be in the span of V T V up to T k minus 1 V, and therefore, we can write it as a linear combination, right. So, if A0 V plus A1 T V plus AK minus 1 T k minus 1 V plus T k V is equal to 0. Suppose this is the 0 vector, suppose this is the linear combination that gives us minus of T k V, then the characteristic polynomial of T restricted to W is given by minus 1 to the power k times A0 plus A1 lambda, is given by G of lambda, which is equal to minus 1 to the power k times A0 plus A1 lambda plus AK minus 1 lambda to the power k minus 1 plus lambda to the power k. Okay, let us give a proof. So, this is a new idea maybe. So, let us see. So, let j be the smallest positive integer such that v t v t square v up to t to the power j minus 1 v is linearly independent. Okay. So, let j be the smallest, largest j be the largest positive integer, smallest would just be j equal to 0. So, that is not useful. J be the largest positive integer such that v t v up to t to the power j minus 1 v, this is a linearly independent set. Right. So, let us put one added assumption in the theorem that V is by a non-zero vector V to just avoid unnecessary complications. Non-zero vector V. When V is 0, there is nothing interesting that happens, because then it will just be the 0 vector. Okay. So, let j be the largest positive integer such that V t v up to t to the power j minus 1 V is linearly independent. Notice that for any value less than j, this is going to be again linearly independent, because it is a subset of a linearly independent set. And also note that then t to the power j V belongs to the span of V t v up to t to the power j minus 1 V. So, remember that t to the power j V means that t applied to t v applied. So, t applied to t applied to t applied to finally t v j minus 1 times, right. So, that is what t to the power j V means, and that is in the span of V to V t v up to t to the power j minus 1. Okay. So, let us assume that, so we will prove that, so the claim is that T L V belongs to the span of V T V up to t to the power j minus 1 V for all L greater than or equal to j. So, we will prove this by an induction argument. So, we already know that t to the power j V belongs to the span. So, let us prove by induction. So, let us assume that the claim is proved for up to L minus 1. So, we will prove that t to the power L V also belongs to the base case, where L is equal to j has been here. The base case, remember, is L is equal to j. Let us now prove that t to the power L V also belongs to the span. But then t to the power L V is nothing but t acting on t to the power L minus 1 V by the very definition of t to the power L V. And we know that t to the power L minus 1 V belongs to the span of, should have given it some name so that I did not have to write it down so many times, but that is okay. But that implies t to the power L minus 1 V is equal to maybe B1 V plus or B0 V plus B j minus 1 T j minus 1 V, and hence t to the power L V will just be equal to B0 T V plus Bj minus 2 Tj minus 1 V plus Bj minus 1 times Tj of V. But Tj of V, you already noted, belongs to the span of V Tv up to t to the power j minus 1 V, and therefore, that will be a linear combination of these vectors. Therefore, this belongs to the span of V Tv up to t to the power j minus 1 V, and therefore, we are done. But what does that mean? This means that t to the power L V belongs to, I should have really written a V to t, I should have really written a notation for it. This for all L, which implies that, what is the name given for the T cyclic subgroup? It is called W. That means that W is contained in span of V1 to Tj minus 1 V. But this is again contained in W, because each of these are in W, and therefore, the span should be contained in W. Therefore, span of V1 to Tj minus 1 V is equal to W, which has, okay, we will come to that. So, what do we know now? We know that V Tv up to t to the power j minus 1 v is both a spanning set and linearly independent, and therefore it is a basis. Hence, v to t to the power j minus 1 v is a basis of W. What do we know about the basis of W? We know that it has k elements. Since dimension of W is equal to k, we have j is equal to k, and we are done, because recall what we were trying to prove. We were trying to prove that V Tv up to t to the power k minus 1 v is a basis of W, and that is precisely what we have ended up proving. We are not done, we have to prove the second part, this part. We have to show, or we have to get explicitly how the characteristic polynomial will look like. Okay, so to do that, again let us look at what we know about V, Tv and so on. Notice that T of T L V is equal to T L plus 1 V for L is equal to 1 to 0 to. So, t to the power 0 by convention is the identity map. So, this will be up to k minus 1. In fact, it is for all. Okay, so let me not write it this way. Let me just say that let t to the power kv be equal to a0 or minus of, let me put it that way, a0 plus a0v plus a1 tv plus up to ak minus 1 tk minus 1 v. Suppose this is the linear combination which gives us minus t to the power kv. Then a0 v plus, then let us see then what happens. What is the matrix of T going to look like? Then we are interested in the matrix of T restricted to W, right? And we know explicitly how this matrix will look like with respect to beta, where beta, I should have given it from the beginning. So let me give it a name now. For beta equal to V Tv t to the power k minus 1 v. Suppose beta is this. Let us look at what is T restricted to W beta beta. So, what is Tv? Tv is the second vector in the basis, right, in the ordered basis. So, you notice, let me just write it for you. The first column will be the image of V, which is going to be 0, 1, 0 up to 0 all the way down. And similarly, Tv is sent to T2V, which will be a 0 here, and so on. And Tk minus 1 will, Tk minus 2 will be sent to, this is the k minus 1th basis vector, or where is Tk minus 2 of V being sent. Tkv is where we will have to worry about. Tkv will just be sent to minus of A0, minus of A1, minus of ak minus 1. So, this is exactly what the matrix of T restricted to W will be with respect to beta. Okay, so let us see what is the then the characteristic polynomial. Let us call it G. G lambda is given by determinant of this matrix minus lambda times ik, which is just going to be equal to, let me write down the matrix explicitly. So, I know what the matrix is from here. This will be minus of lambda 1 0 all the way down, 0 minus lambda, 1 0 all the way down, minus lambda and a 1, and then there will be minus a0 up to ak minus 2 minus of ak minus 1 minus lambda. This is precisely what our expression will look like. So, we will prove that so let us do a cofactor expansion along the first row. This is just going to be equal to minus of lambda times the determinant of, so the first row and the first column is deleted, and what remains is this, then there will be a 0 minus lambda, 1 0 and so on, and finally there will be a minus of a1 to minus of a k minus 1 minus of a k minus, sorry, a k minus 2, and then there is a m k minus 1 2 minus lambda. And how about the last term? So, there are k vectors. So, this is just going to be minus 1 to the power k plus 1 or k plus 1 times minus of a0 into the determinant of, by deleting the first row and the last column, which will just turn out to be 1s in the diagonal, 0 below, minus lambda in the off diagonal, and then 0 here, and the determinant here will just be equal to 1. So, this is equal to the determinant of a upper triangular matrix will just turn out to be the product of its diagonal entries. Then what do we do about the first term here? We will use an induction argument, which I will allow you to complete. By an induction argument, this will be equal to, now in this case it is going to be minus 1 to the power k minus 1 times. So, let us see, this one starts from a1. So, this is going to be a1 plus a2 lambda plus a k minus k does not make sense, this is a k minus 1, a k minus 1 lambda to the power k minus 2 plus lambda to the power k minus 1, and the term here will just be equal to minus of 1 to the power k plus 2, which is the same as minus of 1 to the power k times a0, and this is nothing but the minuses will add up. This will be a minus of 1 to the power k, the a0 will come here, and the lambda multiplied will give you a1 lambda plus up to a k minus 1 lambda to the power k minus 1 plus lambda to the power k, and we are done. So, when our subspace W is the T invariant subspace generated by a vector V, we know exactly what the characteristic polynomial of T restricted to W will look like. Okay, so now we have all the ingredients that are needed to prove the celebrated Cayley-Hamilton theorem. So, to do that, let me just develop a few notations. So, given a polynomial, say p of lambda, which is equal to a0 plus a1 lambda plus a n lambda to the power n, we define p of t to be equal to a0 I plus a1 t plus a to the an t to the power n, and therefore, and thus what is the meaning of pt acting on a vector v? This is just going to be equal to a0 I acting on v, which is equal to v, plus a1 acting on tv plus up to an acting on t to the power nv. So, this is going to be a linear combination of v, tv up to t to the power nv. I will leave it as an exercise for you to check that Pt Qt of v is equal to Qt Pt of v for all v in capital V and polynomials p comma q. Yeah, it is quite straightforward. I will leave it as an exercise for you to check that. Okay. Now, let us state and prove the Cayley-Hamilton theorem. The Cayley-Hamilton theorem broadly tells us that any linear operator satisfies its own characteristic polynomial. So, let me write it down in words. So, let V be a finite dimensional vector space and T be a linear operator on V with characteristic polynomial f of lambda. Then f of t, which we have defined a few minutes back, is the 0 operator. It is the linear transformation which sends every vector v to 0. Informally, we say that t satisfies its characteristic polynomial. So, let us give a proof of this. So, enough to show that for given a vector v, enough to show that given a vector v in capital V, f of t v is equal to 0. That is all. So, if we do that by choice, our vector v is arbitrary, right. So, this will be satisfied for every v. Okay, so how do we go about doing this? So, to do this, let W be the cyclic T cyclic subgroup, sorry, T cyclic subspace generated by V. So, what do we know about the characteristic polynomial of T restricted to W? Then W is invariant. First observation is that W is invariant under T, and suppose A0 plus A1, so A0 V plus A1 V plus AK minus 1 Tk minus 1 V plus T to the power k V is equal to 0, then G of lambda equal to minus 1 to the power k times A0 plus A1 lambda plus up to lambda to the power k is the characteristic polynomial. T restricted to W. But what do we know about G of T V? So, let me write it as star here. Star can be rewritten as G of T acting on V being equal to 0, the 0 vector. And we also proved that if W is a T invariant subspace, then the characteristic polynomial of W divides the characteristic polynomial of T. Sorry, characteristic polynomial of T restricted to W divides the characteristic polynomial of T. So, let f of lambda be the characteristic polynomial of T. Then, by a theorem above, where x is a polynomial, say p of lambda, such that f of lambda is equal to p of lambda times g of lambda, where g of lambda is the characteristic polynomial of T restricted to W. And hence, what is going to be f of T V? That is just going to be equal to P of T times G of T of V. But this is already equal to 0. This is equal to P of T, the operator acting on the 0 vector. But any operator takes, any linear transformation takes 0 to the 0. Therefore, this is equal to 0, and hence f of T is the 0 operator. That is the completion of our proof. So, I would like to conclude by observing that if we stated Cayley-Hamilton theorem as the following: let A be an n cross n matrix and f of lambda be the characteristic polynomial of A, then f of A is equal to 0, where a to the power n is the product of A with itself n times, and f of A is just the polynomial expression which involves a to the power n, a to the power n minus 1 and up to identity.